reactions in the human body. Without them, you're just a pile of chemicals in a bottle of water, and nothing's going to happen. In fact, there's one theory that life on Earth started in a pool of water where there's some organic material, some carbons and some hydrogens and stuff and oxygen, and electricity came along through a storm or friction, and that was enough energy to create life, a little bit of life's, spark. Almost similar to, shocking someone's heart when it's not acting quite right, right? And so that energy came in, and it created organic material that was living, and then over many millions of years, it evolved into what we see around us now, right? So it's just some carbon, some oxygen, some hydrogen, some sulfur, some phosphorus, some of those organic compounds coming together, and then all of a sudden we have life with the help of a lightning bolt or static electricity or something like that. So we have all of these things. Like if we're a whole collection of chemical reactions, we need to control them. We need to speed them up sometimes. We need to slow them down. You're exercising, and you need to convert your stored sugar into free sugar or create ATP, right? If you're exercising, you need to cool down. You need to sweat more, right? You're exercising. Your blood pressure goes up. We need to somehow lower your blood pressure. All of those things. So we can't run high all the time. We can't run low all the time. We have to adjust things on the fly. And we adjust things on the fly a bunch of ways. So ROR is the rate of reaction. And we can slow down or speed up an enzyme's activity so that the rate of reaction goes up or the rate of reaction goes down by controlling these 6 things. Substrate concentration, enzyme concentration, temperature, pH, enzyme inhibition, and enzyme cofactors. Okay, so let's take a look at these 6 things and see how by changing these things we can change the chemical reactions in a human body or an organism's body. For us, it's human anatomy physiology. Okay. So the first one we're going to look at is substrate. Remind me, is substrate the stuff that goes into a chemical reaction or the stuff that comes out? Yeah, it's the stuff that goes in. So let's pretend we got this substrate, right? And this substrate, under ideal conditions, will turn from a yellow ball into 2 red ones. So is that anabolic or catabolic? It's a catabolic reaction, right? What's the chemical reaction called? Hydrolysis. Wow, 2 for 2. So it's hydrolysis. So we use water. Hydrolysis actually means water to cut. So we inject water into this compound, and it splits it into 2. Okay, into the 2 monomers. So that's it. This chemical reaction is a decomposition reaction. It takes this and breaks it into 2. It's a catabolic reaction. It can happen all by itself, but it's really slow. So what we can do is we can introduce an enzyme. If an enzyme comes and touches this, it'll hold it in the right alignment, and bang, it'll split into this really easily. So if I take some substrate, one substrate, and put it in here, we could wait forever and ever and ever, right? But if I take an enzyme in there, we just have to hope that the yellow and the black touch each other, doink, and then it splits into 2 reds. Okay? So that's what the chemical reaction is, and that's how the enzyme works, for example. Now, we can increase the number of red balls appearing for every yellow ball that gets touched by doing what? Well, by adding more substrate, right? So if I put in more substrate, the black enzyme is likely going to run into yellows and turn into reds more often. The example I like to talk about is who watched Charlie and the Chocolate Factory? Yeah, what was the dad's job? Do you remember what the dad's job was before he got fired? Huh? Yeah, it was toothpaste. He put the lid on toothpaste. You remember that? He is the enzyme. He's an anabolic reaction. He's taken a tube of toothpaste and he's putting the cap on the tube of toothpaste. So he's putting stuff together. And he alone could do the chemical reaction. And how fast was he? Well, he was as fast as that tube came down the conveyor belt. You remember? He'd wait for it, grab it, put the lid on it, put it back down, and then wait for another one. So how much substrate did he have? Was it lots or a little bit? It's little, right? He had to wait for it. He did it, and then he waited. Then he did it, then he waited. And then later on in the movie, they sped it up, and he was getting faster and faster, right? And that's because they gave him more and more substrate. So his rate of completion went up. Went up and up and up. Now, so this is what it looks like, right? So this is him putting on lids as they come really slowly. And then as they gave him more and more toothpaste to put lids on, he went faster and faster and faster. But we often see this plateauing. Because if I keep throwing in more and more and more yellow, can this enzyme split faster and faster and faster? No, it's kind of like Charlie's dad. He can only go as fast as his little hands work. So if you give him more and more toothpaste, he's just gonna look and say, "That's going too fast," and he maxes out. And then his rate of reaction just levels out. And then the toothpaste with no caps grow higher and higher and higher and higher, right? And in the movie, they eventually get a machine to do it, and then he's out of a job. I don't know if you remember that. So this is putting caps on faster and faster. They're coming faster, and they're coming faster, and then he maxes out, and he can't go any faster. And that's what we see. Well, we can solve that problem. We can solve that problem by adding more enzyme. So if I want a chemical reaction to speed up, I can put more substrate in. If I want to slow it down, I can take away substrate. Another thing I can do to speed it up is add more enzyme. So if I have that many yellow substrates, and for every time a black enzyme touches it, turns into 2 of those, I can add more enzyme. And it should go faster and faster. So one way they could have helped Charlie's dad was to hire more people, right? And he could have had 3 or 4 people working on that one line, and they go faster and faster. And then their rate would go up and up and up as well. So there's a shorthand here. So square brackets means increase, or sorry, concentration, sorry. That means increase. Now, in fact, it should actually be up arrow. Square brackets are round enzyme, and it would be increase concentration enzymes equals up arrow rate of reaction. So if you're taking chemistry, we usually do that shorthand. Yeah. So more enzyme equals more reactions. And take a look at this graph. So if I keep adding more enzyme with unlimited substrate, it should go up and up. More workers, more workers, more workers. We get faster and faster and faster. What if we don't have unlimited substrate? Does it flatten out? Or does it drops right off, actually? We run out of stuff to do. If we have so many people working, and then all of a sudden the amount of toothpaste tubes are coming so slow because there's so many workers, we could actually run out of toothpaste tubes eventually. There's no more toothpaste tubes. There's so many of us, and we've done so many of them, we're out. And a good example of that, and I think some of us have done this, like if you've ever skipped lunch or dinner or breakfast, and you're working out or running or dancing or something, and you bonk, you hit a wall, and you just can't do anymore, you've run out of your reserve of energy, right? And that's called bonking. So this is increasing rate of reaction with increasing enzyme concentration, but this is with unlimited substrate. If we had limited substrate, we'd run out, and it'd go straight down after a while. You'd run out. So we can speed up chemical reactions by adding more substrate or adding more enzyme. We can slow them down by taking away substrate or taking away enzyme. Another one is temperature. What's the optimal temperature for most chemical reactions in the human body? It's actually higher than that. It's slightly higher. So when you get a fever, your body is actually fighting the fever by doing these really important chemical reactions a little bit faster. Now, the reason why we don't run around with fever, though, is because it really sucks all your energy out of you. So you couldn't go a full day, right, running a fever. You'd be really lethargic and tired all the time. So we run at 37 degrees, which is a good temperature for most chemical reactions to happen, and you can keep functioning. But if you get sick with a cold or flu and you have a mild fever, 37.2, 37.3, 37.4, most of the time we give you an antipyloric, which is like Tylenol or aspirin to lower your temperature. But in fact, it's better to just stick out your low-grade fever because you'll beat the virus or bacteria a little bit better, a little bit more effectively. Now, if you get a runaway fever and you go like 37 to 38 and 39, you're going to die, right? And you need to take your medicine, or you need to actually be submerged into cold water to lower your body temperature, because you could die from extreme fever. But temperature, they usually work right around that magic number of 37 degrees. If you cool it down, the enzyme becomes less flexible. So that induced fit model doesn't work so well, and its effectiveness falls off. The same thing happens when you heat it up. When you heat it up, it starts cooking, and we call that denaturing. So of these two, one's worse than the other. If you deactivate it, can you reactivate it? Yeah. There's a saying, if you take first aid or you're a doctor or a paramedic or a nurse, there's no such thing, there's a saying, you're not dead until you're warm and dead. So if I pull you in from an ocean or a lake or a river that's really cold, or from a snowbank, and you have no pulse, right? We can't see your chest rising. We can't hear anything from your heart. We have to warm you up before we can declare you dead. Okay, unless it's really obvious. Unless we pull you out of the ocean and you're in a block of ice, right? Or we pull you from the snowbank and you actually are decapitated, something like that. It's got to be really obvious. But if you're just sitting there, laying there as a cold body and we can't feel your pulse, we have to warm you up first, because those chemical reactions can start again. There could be a minor little heartbeat that we can't hear, right? Your chest could be rising really shallow. And then when we warm you up, the chemical reactions can kick in and we can actually see it. And we do this all the time, don't we? Someone needs a heart transplant. We take the heart out and we put it on ice, right? Liver transplant. Or you cut your did you hear the story about that woman in Europe somewhere? I think it's Slovenia. She cut off her own hand for insurance reasons. It was just in the news. She cut off her own hand because she had $1 million in insurance. So her boyfriend and her cut off her hand, and they did it on purpose, and they left it in the field on purpose so that they couldn't find it, because she would get $1 million if she lost a limb, and they couldn't reattach it. And they found it. They found it and reattached it, so she has this hand now that doesn't quite work. And then there was a lawsuit by the insurance agency, and they found out that they had planned it. They had planned to cut off her arm for $1 million. Her hand, actually, so not her arm. And she denies it, obviously. But anyway, one of the reasons they knew that she was probably planning it is because the Google searches. It's like, Google search, what limb should we cut off? How should you cut it off so they don't bleed to death? And like, how many hours before you can reattach it and all this stuff. And that was all the searches that they had done prior to her rushing to the hospital and having her arm, partially amputated or fully amputated hand from a circular saw. So one of those giant circular saws. Yeah. Anyways, if you deactivate it, it can be reactivated. If you denature it, you can't renature it. What's a good example of denatured protein? An egg. You cook an egg. You've denatured the protein. Now imagine your mom, you're in a rush and you're like, I can't have my breakfast today. And your mom's, I made you an egg. Oh, I guess I'll just uncook it and we'll have it tomorrow. You can't do it, can you? It's very difficult to uncook an egg. It's been done. There's labs that do it, but it's very difficult, right? Because when you cook protein, it just turns into fibers, and to uncook it, you have to untangle the fibers. So they've uncooked eggs in labs. I usually show the video, but it's not very exciting actually. But it's neat because it's scientific, but it's not very exciting. So there you go. Optimal temperature, 37. If you get too warm, see how the rate of reaction falls off. If you get too cold, see how the rate of reaction falls off. The nice thing about too cold, though, is you can heat it up, it can work again. If you cook it and you cool it down, it's still cooked. Yeah? So, very similar to pH. pH is the optimal acid level or base level in a tissue for enzymes to work. Usually around 6 to 8, right? in your stomach, the pH is around 1 to 2. And this enzyme pepsin, which helps digest proteins, works best at pH 1 or 2. Then you got trypsin, which also digests proteins, but in your small intestine, and its optimal pH is actually 8.5. So basic. Blood is around 7.5 pH. So what happens? If you change the pH too much, extremely to the acid or extremely to the base, it denatures the protein, right? And I think you've seen this. Lots of, I think it's South Americans, I think, or it's the Spanish. They like to cook stuff in lemon juice and lime juice, acid, right? So you can cook stuff with acid. And if you've ever had an acid burn, like spilled some acid on your skin, not just vinegar, but like, hydrochloric acid or something, you can feel it. It actually burns. And so does base burns. Base burns are even worse. These base burns, they get in there and they start dissolving fat. And that's why we use bases for cleaning ovens. And it'll get underneath your skin and start dissolving your fat underneath your skin. And that's why, base burns are all pretty bad, So there you go. There's pepsin on the left. It likes to work around pH 1. Trypsin digests the same thing, proteins. But in your small intestine, its optimal pH is 8. And for blood and tissue, it's around 7 to 7.5. So, any questions? So we can speed things up. Speed them up how? We can speed them up by adding more substrate. Add more enzyme, heating it mildly, right? A little bit greater than 37. We can also optimize its pH. Change the pH a little bit closer to its optimal. We can slow them down by taking away substrate, taking away enzyme, cooling it down, and we can also change the pH. Okay. Another method to control enzymes working, speeding up and slowing down, is by adding inhibitors. Now these are molecules that bind to enzymes and block the substrate from binding, or they can bind somewhere else and change the shape of the active site. So there's two types. They're called competitive inhibition and non-competitive inhibition. Our example would be musical chairs. Anyone play musical chairs? Right? Yeah, and you're going around, there's 6 people, 5 chairs, and the music turns off, and then 5 people get it because they're all competing for the same chair. They're all competing for the same active site. So they're trying to sit in the same spot. If they sit in the same spot, you can't sit on it, so it's taken. That's competitive inhibition. Competitive inhibition is when there's a chemical, and it could be a poison, like a toxin. It can be a heavy metal. It can be like a venom from a snake or a spider, right? It can go in there, and it can block the active site. So this is what's supposed to happen. Yellow substrate fits in there, and then it breaks up into a Pac-Man and a diamond. Is that catabolic or anabolic? Catabolic. But instead, you have this inhibitor in there. And it could be lead, right? It could be cadmium. It could be Novichok, that poison that the Russian guy got, right? It can be arsenic. It can be snake venom. It could come in there and block the active site. And now, circle diamond won't fit in there. So the chemical reaction for circle diamond, catabolic splitting into circle, Pac-Man and diamond, doesn't happen. Can't do it. Now this can be reversible or irreversible. Sometimes this can poop out. And if this releases, can this guy come in? Yes, that's called reversible. But there are ones that combine and never let go. Those are called irreversible inhibitors. Okay, so which one do you think is worse? Reversible or irreversible? Irreversible is very bad. A good example of that, it's not quite exactly the same, but carbon monoxide poisoning. If you inhale carbon monoxide, it will bind to your hemoglobin of your blood, and it's irreversible. It doesn't want to come off. So the only way to like, if you see someone, they're like carbon monoxide poisoning, and you pull them out, and you bring them to fresh air, it might not be enough. Because every time they inhale, exhale, the blood will come to the lungs, the carbon monoxide stays and goes back around again. So you have to put them in a hyperbaric chamber, which forces the oxygen in, or you have to give them a blood transfusion. and take out the naughty blood and give them some good blood. And that's irreversible. The second type is non-competitive. So this is musical chairs again, right? You sit in the spot, you get to change. But instead of competing for the seat, what happens is this thing comes along and throws some tacks on the chair, so you don't want to go on it. So they don't actually fight for the same spot. They do something else somewhere on the enzyme, and the enzyme, the active site changes. So either the active site changes so much that the substrate can't go there, or it changes a little bit so it doesn't work as well. Now again, this can be reversible or irreversible. Okay? And you can decide if that's, you know which one's worse. The irreversible is worse. But it changes it so that it doesn't work as well. Okay? So that's another way to speed up or slow down a chemical reaction. Add poisons in. That will slow it down. The last thing we have to talk about, and we chatted about this before, is enzyme cofactors. Right? If you're missing these vitamins and minerals that help the enzyme working, then the rate of reaction falls. So if you need vitamin C so you don't get scurvy, right, and you take away all the vitamin C, those chemical reactions that require vitamin C stop, or they slow down. Right? And that could be minerals as well, like iron, copper, right, potassium, sodium, and it can include organic stuff like vitamin A, vitamin C, vitamin D, vitamin E, stuff like that. Okay, any questions? So that's how we control the rate that enzymes work. All right, good.